Hi viewers, welcome to my tutorial class on composite bars. In today's class, we'll work out another example on composite bars. A load is supported by two copper rods and a steel rod. If the stresses in copper and steel are not to exceed 40 MPa and 90 MPa respectively, find the magnitude of safe load that can be supported. Take ES is equal to 2 times EC. So in this example, a load has to be supported by two copper rods and a steel rod. This copper rod is having equal area of cross section and its cross section is given as 40 by 40 mm square. That means it is having a square cross section 40 mm by 40 mm size. Steel is having a cross section 30 mm by 30 mm. So the cross section area will be 30 into 30 or 900 mm square. The constraints given are the stress in copper not to exceed 40 MPa and stress in steel not to exceed 90 MPa. With this condition, we have to find out the maximum load that can be supported by these three rods. And you are also given that Young's modulus of steel is equal to twice the Young's modulus of copper. We have to assume that load position is adjusted in such a way that it remains horizontal. That means all the bars will reduce the length by equal amount. The data given is tabulated here. AS is 30 into 30, that is 900 mm square, that is area of steel rod 900 mm square. Area of copper rods is 40 into 40 into 2, because two copper rods are there. The total area of cross section supporting this load is 40 into 40 into 2, that is 3200 mm square. And also you are given that ES is equal to 2 times EC and length of steel rod is 300 plus 200, that is 500 mm. Length of copper rods is equal to 300 mm. And you have to find out the maximum load that can be supported without exceeding the stress limits given in steel and copper. So in steel you are given 90 MPa stress limit and copper 40 MPa. These values given are maximum that is permitted for these materials. So when the load is placed, the stress values in both the materials should be within these limits. It should not cross the given values. Now let us work out. We assume that the load is placed in such a way that all the bars are getting compressed equally. So that means the load is remaining in the horizontal position. So each bar will deform equally and the reduction in length in each bar will be equal. So you can write delta LS is equal to delta LC. That is, reduction in length in steel is equal to reduction in length in copper. Now delta LS is strain multiplied by length. So strain is sigma S by ES for steel. Strain in steel is sigma S by ES into LS is equal to sigma C by EC. So that is strain in copper into length of copper rod. So here LS is not equal to LC, so that will not cancel. So reduction in length in both the materials are equal, but strains are not equal because this reduction in length is in different length of the bars. So strains are not equal. So you can find out sigma S as ES by EC into LC by LS into sigma C. So this will give the relationship between the stress induced in steel and copper. ES is given as 2 times EC, So I have substituted ES as 2 EC, and LC is known 300 and LS is 500. So EC get cancelled, 2 into 300 by 500. So that is 1.2 sigma C. So stress in steel has to be 1.2 times stress in copper for this relationship of Young's modulus and the length of rods. So there are two factors. One is the ratio of Young's modulus, that is modular ratio, and another one is ratio of lengths. So for these given values, the stress in steel has to be 1.2 times the stress in copper. So this relation should be always true while supporting the load. Also, you are given the two constraints. The stress limits for copper and steel is given, safe values of stresses. So this can be considered as safe values of stresses, because we are given that stresses should not exceed 40 and 90. In copper and steel, the stresses are not permitted to exceed 40 and 90. So these are safe values of stresses, and also this relation should be satisfied. Sigma S is equal to 1.2 sigma C. Now let us permit the stress in copper to its maximum value, 40 megapascal. So when stress in copper is 40 megapascal, stress in steel will be 48 megapascal. 1.2 times 40, 48 megapascal. And this is less than the safe value of stress, which is 90 megapascal. So these stress values are okay. On the other hand, if you allow the stress in steel to go to 90 megapascal, which is permitted for steel because safe value of stress for steel is 90 megapascal. So if you allow the stress in steel to 90 megapascal, corresponding stress in copper will be 90 by 1.2. Okay, as per this relation, 90 divided by 1.2, you will get stress in copper as 75 megapascal, which is more than the safe value of stress for copper, which is 40 megapascal. So 75 is greater than 40, so you cannot allow the stress in copper to go to 75 megapascal. So even though steel can take up 90 megapascal, we cannot allow that stress because corresponding stress in copper will be 75 megapascal. So these values are not possible, because always this relation should be satisfied. Even though steel can take this value, when steel takes this stress in copper will be greater than the permissible limit. So this cannot be allowed. So you should restrict the stresses to 40 megapascal in copper and 48 megapascal in steel. So the stresses we understood, sigma C is 40 megapascal and sigma S is 48 megapascal. Both are safe now. Copper, it has reached its maximum safe limit, but steel it is less. But you cannot allow more than this, because if you allow the stress in steel more than this, stress in copper will exceed. So after getting the stresses, you can find out the load that can be supported, P as PS plus PC. So that is P is equal to sigma SAS plus sigma CAC. You can substitute for sigma S and sigma C. Sigma S is 48, AS is also known 900 mm square, and sigma C is 40, and AC for both the rods it is 3200. Substituting that, you will get 171.2 into 10 raised to 3 Newton, or 171.2 kilonewton. So this is the maximum load these rods can support by satisfying the given condition. So that's all for today. Thank you for watching.